For a 20 amp circuit, the neutral conductor should also be sized at 20 amps. This ensures that the neutral can safely carry the maximum potential unbalanced load. You only need one equipment grounding conductor in the conduit, regardless of the number of circuits. The minimum size for the equipment grounding conductor is number 10 AWG copper. This is in accordance with the National Electrical Code. To determine the appropriate conduit size, you need to calculate the total number of conductors within the conduit. For each 120-volt circuit, you have two current carrying conductors, which are the hot and neutral, and one equipment grounding conductor. Therefore, for two circuits, you will have a total of 6 conductors. That is 4 current carrying conductors plus 2 equipment grounding conductors. Refer to Chapter 9, Table 1 of the National Electrical Code to determine the conduit size based on the number and size of conductors. As a general guideline, a 1-inch conduit is typically sufficient for up to 7 conductors. Always consult the NEC for the specific conductor types and conduit sizes being used, as this can affect the fill capacity. The distance of the conduit run does not directly affect the sizing of the neutral or ground conductors. However, the length of the run is a critical factor in calculating voltage drop. Excessive voltage drop can cause equipment malfunction and potential safety hazards. Calculate the voltage drop for each circuit to ensure it remains within acceptable limits at the furthest outlet. Use the appropriate formula or voltage drop calculators to determine the voltage drop based on wire size, current, and distance. If the calculated voltage drop exceeds the recommended limit, which is typically 3% for branch circuits, you may need to increase the conductor size to reduce the voltage drop. For 120 volts branch circuits, it is often recommended to keep the voltage drop below 3.6 volts to ensure proper operation of connected equipment. Here's a more detailed explanation of the concepts involved in sizing conductors and conduits for electrical installations. Let's start with neutral conductors in multi-wire branch circuits. In a multi-wire branch circuit, a single neutral conductor is shared by 2 or more hot conductors. This arrangement can save on wiring costs, but it's crucial to size the neutral conductor correctly. The neutral conductor must be sized to carry the maximum possible unbalanced load. The unbalanced load is the difference between the current flowing through the hot conductors connected to the neutral. For example, if you have 2 20-amp circuits sharing a neutral, and one circuit is loaded to 15 amps while the other is loaded to 10 amps, the unbalanced load on the neutral would be 5 amps. However, you must size the neutral based on the maximum potential load of each circuit. In this case, the neutral must be rated for at least 20 amps because each circuit is protected by a 20-amp breaker. In some situations, the neutral conductor may need to be oversized. This is especially true for circuits that serve nonlinear loads, such as electronic devices with switching power supplies. Nonlinear loads generate harmonic currents that can cause the neutral conductor to overheat if it is not sized appropriately. Consult the NEC for specific requirements regarding neutral conductor sizing for nonlinear loads. Now let's discuss equipment grounding conductors. The equipment grounding conductor provides a low impedance path for fault current to return to the source. This helps to quickly trip the circuit breaker or fuse, preventing electrical shock hazards. As mentioned earlier, you only need one equipment grounding conductor in the conduit, regardless of the number of circuits. However, the equipment grounding conductor must be sized according to the size of the overcurrent protection device protecting the circuit. Table 250.122 in the NEC provides guidance on sizing equipment grounding conductors. For a 20-amp circuit, a number 12 AWG copper equipment grounding conductor is typically sufficient. However, for longer runs, you may need to increase the size of the equipment grounding conductor to reduce impedance and ensure effective grounding. The equipment grounding conductor must be connected to all metal enclosures, boxes, and equipment associated with the electrical system. This helps to create a continuous ground path and minimize the risk of electrical shock. Let's move on to conduit sizing. Conduit protects the conductors from physical damage and provides a raceway for pulling the wires. The NEC specifies the maximum allowable fill for different types of conduit. Fill is the percentage of the conduit's cross-sectional area that is occupied by the conductors. Chapter 9, Table 1 of the NEC provides the maximum number of conductors allowed in different sizes of conduit. To determine the conduit size, you need to calculate the total cross-sectional area of all the conductors. The cross-sectional area of a conductor can be found in Chapter 9, Table 5 of the NEC. Once you have calculated the total cross-sectional area of the conductors, you can refer to Chapter 9, Table 4 of the NEC to determine the minimum conduit size required. It is always a good idea to use a slightly larger conduit size than is required to make it easier to pull the wires. Overfilling the conduit can damage the conductors and make it difficult to pull them. In addition to the number and size of conductors, other factors can affect the conduit size. These include the type of conduit, the number of bends in the conduit run, and the presence of any fittings or couplings. Always consult the NEC for specific requirements regarding conduit sizing. Finally, let's discuss voltage drop. Voltage drop is the decrease in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment malfunction, reduce the efficiency of electrical equipment, and create safety hazards. The NEC recommends that the voltage drop on branch circuits should not exceed 3%. To calculate voltage drop, you can use the following formula: voltage drop equals 2 times K times I times D divided by Cm, where K is the direct current constant, which is 12.9 ohms for copper and 21.2 ohms for aluminum. I is the current in amps, D is the one-way distance in feet, and Cm is the circular mils of the conductor. The circular mils of a conductor can be found in Chapter 9, Table 8 of the NEC. If the calculated voltage drop exceeds 3%, you need to increase the conductor size to reduce the resistance and lower the voltage drop. You can also reduce the voltage drop by shortening the length of the circuit or reducing the current. Consider using a higher voltage system, such as 277/480 volts, for long runs to minimize voltage drop. Remember to consult the NEC and local electrical codes for specific requirements and guidelines related to electrical installations. It is always best to consult with a qualified electrician for any electrical work to ensure safety and compliance. To further clarify these concepts, let's consider a specific example related to the classroom wiring project. Assume each classroom requires 2 quad outlets, with each quad outlet fed by 2 20-amp circuits. This means a total of 4 20-amp circuits per classroom. First, let's determine the neutral conductor size. Since each circuit is rated at 20 amps, the neutral conductor must also be rated for at least 20 amps. If the circuits are sharing a neutral in a multi-wire branch circuit, the neutral conductor must be sized to carry the maximum potential unbalanced load. In this case, the neutral should still be rated for 20 amps per circuit. Second, let's determine the equipment grounding conductor size. According to NEC Table 250.122, a 20-amp circuit requires a number 12 AWG copper equipment grounding conductor. However, since the conduit run is 155 feet, it may be prudent to increase the size of the equipment grounding conductor to reduce impedance. A number 10 AWG copper equipment grounding conductor would provide a lower impedance path and improve grounding effectiveness. Third, let's determine the conduit size. Each circuit consists of 2 current carrying conductors, which are the hot and neutral, and 1 equipment grounding conductor. Therefore, 4 circuits would have a total of 12 conductors. That is 8 current carrying conductors plus 4 equipment grounding conductors. Refer to Chapter 9, Table 1 of the NEC to determine the appropriate conduit size for 12 conductors. Depending on the specific type and size of conductors used, a 1 1/4 inch or 1 1/2 inch conduit may be required. It is important to carefully calculate the conduit fill to ensure compliance with the NEC. Finally, let's calculate the voltage drop. Assuming each circuit is loaded to 16 amps, which is 80% of the 20 amp breaker rating, and the wire is number 12 AWG copper with a length of 155 feet, the voltage drop can be calculated using the formula mentioned earlier. Voltage drop equals 2 times K times I times D divided by Cm, where K is 12.9 ohms for copper, I is 16 amps, D is 155 feet, and cm for number 12 AWG copper is 6,530 circular mils. Plugging in the values, the voltage drop is approximately 9.7 volts. This represents a voltage drop of about 8.1%, which exceeds the recommended 3% limit. To reduce the voltage drop, you would need to increase the conductor size. Using number 10 AWG copper wire with a circular mil area of 10,380 would reduce the voltage drop to approximately 6.1 volts, which is about 5.1%. While this is still above the 3% recommendation, it is significantly better. Alternatively, you could reduce the load on each circuit or shorten the length of the run to decrease the voltage drop. Remember to always consult the NEC and local electrical codes for specific requirements and guidelines related to electrical installations. It is crucial to prioritize safety and ensure compliance with all applicable regulations. When in doubt, seek guidance from a qualified electrician. Furthermore, let's consider some additional aspects of classroom electrical installations. Classroom environments often have specific requirements for lighting, power outlets, and technology integration. Lighting should be designed to provide adequate illumination for learning activities while minimizing glare and shadows. Power outlets should be strategically placed to accommodate student devices, computers, and other equipment. Technology integration may involve installing data communication cables, interactive whiteboards, and audio-visual systems. When designing the electrical system for a classroom, it is important to consider the future needs of the space. Classrooms are often used for a variety of activities, and the electrical system should be flexible enough to accommodate changing technology and pedagogical approaches. Consider installing additional conduit and pull boxes to allow for future expansion or modifications. It is also important to coordinate the electrical design with other building systems such as heating, ventilation, and air conditioning. Ensure that the electrical system can handle the load requirements of these systems without overloading the circuits. In addition to the technical aspects of electrical installations, it is also important to consider safety. Classrooms are occupied by students and teachers, and the electrical system must be designed to minimize the risk of electrical shock, fire, and other hazards. Install ground fault circuit interrupter receptacles in areas where water is present, such as near sinks or drinking fountains. Use tamper-resistant receptacles to prevent children from inserting objects into the outlet. Ensure that all electrical panels and equipment are properly labeled and accessible for maintenance. Conduct regular inspections of the electrical system to identify and address any potential problems. By following these guidelines and working with qualified professionals, you can ensure that the electrical system in a classroom is safe, reliable, and conducive to learning. Remember that electrical work can be dangerous, and it is always best to leave it to the experts. If you are not comfortable working with electricity, hire a qualified electrician to perform the work. Here are some additional points to consider when working with electrical systems. Firstly, always to energize the circuit before working on it. Use a multimeter to verify that the circuit is energized before touching any wires. Secondly, wear appropriate personal protective equipment, such as safety glasses and gloves. Thirdly, use insulated tools to prevent electrical shock. Fourthly, follow all safety precautions and guidelines provided by the NEC and local electrical codes. Fifthly, never work on electrical systems when you are tired or distracted. Sixthly, if you are not sure how to do something, ask for help from a qualified electrician. Seventhly, always double-check your work to ensure that it is safe and correct. Eighthly, keep your work area clean and organized. Ninthly, dispose of electrical waste properly. Tenthly, educate yourself about electrical safety. By following these tips, you can reduce the risk of electrical accidents and injuries. Remember that electricity is a powerful force, and it must be treated with respect. If you have any questions or concerns about electrical safety, consult with a qualified electrician or electrical inspector.